sklearn. Discriminant analysis. Description. Discriminant analysis is a statistical technique used for classification. It aims to find linear combinations of features that best separate different classes. sklearn. Discriminant analysis provides implementations of various discriminant analysis methods like linear discriminant analysis (LDA), quadratic discriminant analysis (QDA), and others. Inputs. X. The training input samples. A 2D array-like structure, e.g. NumPy array. Pandas data frame containing features. Each row represents a sample, and each column represents a feature. Y. The target class labels corresponding to each sample in X. A 1D array-like structure, e.g. NumPy array. Pandas series. Outputs. Model. A trained discriminant analysis model object that can be used for prediction. Predictions. Predicted class labels for new input samples using the trained model. Steps. Data preparation. Ensure your features and target labels are in suitable formats, e.g. NumPy arrays. The data should be preprocessed if needed, e.g. standardization. Scaling. Model selection. Choose the appropriate discriminant analysis method, LDA, QDA, etc., based on your data characteristics and assumptions. LDA assumes equal covariance matrices for classes, while QDA allows for different covariance matrices. Model training. Fit the selected model to the training data using the fit method. Prediction. Use the trained model to predict class labels for new input samples using the predict method. Metrics. Accuracy. Percentage of correctly classified samples. Precision. Proportion of true positive predictions out of all positive predictions. Recall. Proportion of true positive predictions out of all actual positive samples. F1 score. Harmonic mean of precision and recall. Confusion matrix table summarizing the performance of the model by showing true positives, true negatives, false positives, and false negatives. Visualization plots. Scatter plot. Plot the features for different classes to visualize how well the model separates them. Colors can be used to represent classes. Decision boundary plot. Visualize the decision boundary that the model uses to classify samples. This plot can help understand how the model is making predictions. Fine-tune parameters. Solver. The algorithm to use for computing the discriminant functions. Choices include SVD singular value decomposition, eigenvalue decomposition, and LSQR least squares. Shrinkage regularization parameter for the covariance matrices. It reduces the variance of the estimates by shrinking the covariance matrices towards the average covariance matrix. This can be useful for preventing overfitting, especially when dealing with high dimensionality. Prior probabilities of the classes. If not provided, the priors are estimated from the data. Stochcovariance. Whether to store the covariance matrices of each class in the fitted model. This can be useful for later analysis. Uncertainty methods. Confidence scores. Models can provide confidence scores for each prediction, indicating the certainty of the classification. Probabilistic predictions. Some models offer probabilistic predictions, giving the probability of belonging to each class. Challenges and fixes. Challenge 1. Overfitting. When the model fits the training data too closely, it may perform poorly on unseen data. Overfitting can occur in high-dimensional datasets or with limited training samples. Sample use case that resulted in challenge 1. A small dataset with many features resulted in a model that perfectly classified the training data but had low accuracy on a test set. Fixes to challenge 1. Use regularization techniques like shrinkage in discriminant analysis or L1-L2 regularization in other models. Reduce the number of features using feature selection methods. Increase the size of the training dataset if possible. Challenge 2. Data imbalance when one class has significantly more samples than others. The model may be biased towards the majority class. Sample use case that resulted in challenge 2. A dataset with 90 samples belonging to one class and 10 to another resulted in a model that always predicted the majority class. Fixes to challenge 2. Use oversampling techniques like SMOT to increase the number of samples from the minority class. Use undersampling techniques to reduce the number of samples from the majority class. Use cost-sensitive learning methods that assign higher costs to misclassifying samples from the minority class. Challenge 3. Nonlinear data discriminant analysis is a linear method, meaning it assumes linear relationships between features and classes. If the data is inherently nonlinear, it may not perform well. Sample use case that resulted in challenge 3. A dataset with a nonlinear decision boundary between two classes resulted in ELDA failing to separate them effectively. Fixes to challenge 3. Use nonlinear classification methods like support vector machines (SVMs) with a nonlinear kernel, decision trees, or random forests. Apply dimensionality reduction techniques like kernel PCA to transform the data into a higher dimensional space where linear relationships can be found. sklearn, discriminant analysis, quadratic discriminant analysis. Description: a classifier with a quadratic decision boundary, generated by fitting class conditional densities to the data and using Bayes' rule. The model assumes that the data within each class has a Gaussian distribution and uses the mean and covariance matrix of the data to determine the decision boundary. Inputs: X the training input samples. As a 2D array, each row represents a sample, and each column represents a feature. Y the target values class labels for the training samples. This should be a 1D array of integers or strings. Outputs: self the fitted quadratic discriminant analysis object. This can be used to make predictions on new data. YPRED the predicted class labels for new input samples. This is a 1D array of integers or strings, with the same shape as the input data. Steps: initialization: initialize the model with specified parameters. Training: the model learns the mean and covariance matrix for each class in the training data. Prediction: given a new input sample, the model calculates the probability of the sample belonging to each class based on the learned class parameters. The class with the highest probability is assigned as the predicted class. Metrics: accuracy: the proportion of correctly classified samples. Precision: the proportion of correctly classified samples among those predicted to belong to a specific class. Recall: the proportion of correctly classified samples among those that actually belong to a specific class. F1 score: the harmonic mean of precision and recall. ROC AUC: the area under the receiver operating characteristic curve, which measures the model's ability to distinguish between different classes. Visualization plots: decision boundary: a plot that shows the decision boundary separating the different classes. This can help to visualize the model's predictions. Scatter plots: scatter plots can be used to visualize the distribution of the data within each class and to identify outliers. Fine-tune parameters: priors: the prior probabilities of the classes. If not specified, the priors are calculated from the training data. Regparam: a regularization parameter that adds a small value to the diagonal of the covariance matrix to prevent numerical instability. This parameter can be adjusted to improve the model's performance. Uncertainty methods: probability estimates: the model provides probabilities for each class for a given input sample. The uncertainty can be measured by the difference between the highest and second highest. Probability. Challenges and fixes. Challenge 1: the model may overfit the training data, resulting in poor performance on unseen data. Sample use case: a model trained on a small dataset of images may classify images from a different dataset with low accuracy. Fixes. Regularization: use a larger regularization parameter to prevent overfitting. Cross-validation: split the training data into multiple folds and train and evaluate the model on different combinations of folds. Challenge 2: the model can be sensitive to outliers in the data, which can affect the learned class parameters and the decision boundary. Sample use case: a single outlier in the data may significantly shift the decision boundary, leading to inaccurate predictions. Fixes. Data preprocessing: remove or adjust outliers in the data before training the model. Robust estimation: use robust methods for estimating the mean and covariance matrix, which are less sensitive to outliers.